Prove each statement in 8 through 23 by mathematical induction. The square root of n is less than 1 over the square root of 1 plus 1 over the square root of 2 plus ... plus 1 over the square root of n for every integer n greater than or equal to 2. So this portion here is going to be our p of n. The base case is going to correspond to when n equals 2. So we're going to replace all of our n's in this p of n with the number 2. So after replacing my n with 2, I'm going to place a question mark here so that we don't assert the conclusion that we're trying to show. We're trying to prove that this is true. Now, to prove this inequality, I'm actually going to work algebraically from our conclusion. This is technically working backwards from our conclusion, and so we'll have to be a little bit more careful about how we present this proof after we do this algebra from the conclusion. I can multiply both sides of this inequality by root 2 to get 2 is less than root 2 plus 1. And then I could subtract 1 on both sides to get 1 is less than root 2. And that's definitely true. And so if we want to prove the base case, we have to start from 1 is less than or equal to root 2 and then do the algebra to get to this red portion here, which is the base case. The beginning of the inductive step is always the same. Let k be an arbitrary integer with k greater than or equal to 2. And assume that p of k is true. We want to show that p of k plus 1 is true. So let's unpack our inductive hypothesis. This is the thing that we get to assume. P of k is the same thing as p of n, but we replace all of our n's with k. So we get to assume that the square root of k is less than or equal to 1 over the square root of 1 plus 1 over the square root of 2 plus ... and then plus 1 over the square root. Now, normally, with p of k plus 1, I usually start with the left-hand side, which would be the square root of k plus 1. But there's not much I can do algebraically to manipulate the square root of k plus 1 into something involving the square root of k. And so because of that, I'm actually going to start with the right-hand side of p of k plus 1. I'm going to write that out. The right-hand side of p of k plus 1 is going to be 1 over the square root of 1 plus 1 over the square root of 2 plus ... And then I'm going to write the last two terms of this series. The second to last term would be 1 over the square root of k, and then the last term would be 1 over the square root of k plus. Now here we clearly have a portion of the inductive hypothesis. So we can use the inductive hypothesis to show that this is greater than or equal to the square root of k. And I'm going to write that down here. So this whole thing is greater than or equal to square root of k, and then plus that last term over here, which is 1 over the square root of k plus. Now, the goal of this is to show that this is greater than or equal to the square root of k plus 1, which is the left-hand side of p of k plus 1. That's the goal, but this is actually kind of difficult to prove. So to prove this part, we're going to create a separate mini proof here. And to prove this, I'm going to work backwards from my conclusion so that we can eventually work backwards to something that's obvious and true. What we can do to both sides is multiply by the square root of k plus 1. And so this would be the square root of k plus 1 times the square root of k. And then plus 1 is greater than or equal to just k plus 1. I can subtract 1 on both sides. Square root of k plus 1 times the square root of k is greater than or equal to k. Now, why would that be true? Well, the reason that would be true is because the square root of k plus 1 times the square root of k is bigger than the square root of k times the square root of k. If I reduce this value here, then it's going to make the overall value smaller, and this is equal to k. And so we can start from here and work forwards to the conclusion by adding 1 on both sides and dividing both sides by the square root of k plus 1. And this would imply that this inequality is true. And so this is the left-hand side of p of k plus 1. So what we have shown is that the right-hand side of p of k plus 1 equals this thing, which is bigger than this thing by the inductive hypothesis. And we can say this is bigger than the square root of k plus 1 because of this algebra down below here. And the square root of k plus 1 is the left-hand side of p of k plus 1. So to summarize what we've shown that the right-hand side of p of k plus 1 is at least as large as the left-hand side of p of k plus 1. And this is what we wanted to show. This implies that p of k plus 1 is true. P of k plus 1 states that the right-hand side is greater than or equal to the left-hand side. Or specifically, the left-hand side is less than or equal to the right-hand side. It's the same thing, but it's easy to just flip the inequality. So P of k plus 1 is true, which means that P of k implies that P of k plus 1 is true, which means that by mathematical induction, P of n is true for all integers n greater than or equal to 2. Thanks, everyone, and I'll see you in the next